Welcome. My name is Steve Goodnick, and I'm a professor of electrical and computer engineering at Arizona State University, as well as a Hans Fischer Senior Fellow at the Institute for Advanced Studies in the Technical University of Munich. Today, I'm going to talk about nanotechnology pathways to next-generation photovoltaics. So I plan to give an overview, basically of the field of photovoltaics in general, and then talk about how nanotechnology can play a role in basically improving the performance of photovoltaic devices. By way of that, I'm going to follow this outline. I'll provide first an overview of photovoltaics, and then talk about advanced concepts for improving the efficiency of photovoltaics. Many of these are, of course, based on nanotechnology, and I'll explain how nanotechnology can play a role in that. Within that context, I'll talk about light trapping approaches to improving the performance of solar cells, intermediate band and quantum well solar cells, multi-electron generation and nanowire cells, hot carrier solar cells, and finally summarize. So in general, nanotechnology is pervasive in the energy industry. And this chart, which is from basically a commercial review in Germany, this illustrates some of the applications of nanotechnology in various aspects of energy. And this is very broad and probably very difficult to read, so I'm not going to go into detail. But just to say that nanotechnology impacts all aspects of the energy supply chain, from energy generation, energy conversion, the distribution of energy, energy storage, and finally the utilization of energy. I'm going to focus today basically on one aspect of that, which is photovoltaics. And that is, I'm going to talk about solar energy conversion to electricity, and talk about the applications of nanotechnology in that area. But as you can see from this chart, nanotechnology plays a role in various aspects of energy, ranging from the structural components of materials to basically improving the performance of devices, to improving storage devices, and finally, on the end use, some of the applications in terms of smart grid and other information technology applications of nanotechnology that help enable energy utilization. So let me talk first about photovoltaics and explain basically the process. So photovoltaics is the direct conversion of sunlight to electricity, and it's the only direct conversion type of technology that exists. Other forms basically go through an intermediate step, such as solar thermal energy conversion takes energy into heat, but then that heat has to go through another step of turning a steam turbine, for example, to convert that to electricity. Photovoltaics is direct, and the way that occurs is basically, you can think of it as a two-level system, and what's shown in the diagram here is an example of the band diagram of a silicon solar cell. And by band diagram, what I mean is that what I'm plotting here is basically a two-level system. There's a valence band, E sub V, and a conduction band, E sub C, and these are separated by an energy gap. And this energy gap plays a crucial role in basically the performance of solar cells. It's the single most important metric, probably, in terms of the performance of solar cells. So this energy gap basically is the separation between filled states, which are in the valence band, and empty states in the conduction band. And so when a photon, which is a quanta of energy carried by light, is incident on a semiconductor, it's basically absorbed, and the way it is absorbed is that it promotes an electron from the filled states to the empty states here, as shown. And basically it then promotes an electron to an excited state, and it leaves behind an empty state, which we call a hole. Now, both the electron and the empty state, the hole can move, and the electron basically moves in one direction, and the hole moves in the other direction because there's an electric field. In other words, there's a potential energy gradient, which causes the electron to basically want to fall downhill and move in this direction. The hole, on the other hand, moves in the opposite direction, and therefore what happens is you have negative charge moving this direction, you have positive charge moving this direction, and that gives rise to a photocurrent. So that photocurrent then is responsible for the electrical current that can be used to do useful work, such as driving a resistive load or some kind of engine or something. So basically, what's necessary for a photovoltaic device to work is that you have to have charge separation. And that's true not only for photovoltaics, but that's true also for other processes like photosynthesis, in which you create an excited electron, you create an electron hole pair, and that electron does work to do chemistry instead of producing electricity. What you can see is that what's important is that you have an asymmetry at the junction. That is that the electron wants to go one direction and the hole goes the other direction. And it's necessary then to have an electric field at that junction. And that's formed by making what's called a p-n junction, which is a junction between two dissimilar types of semiconductors. One is called p-type and one is n-type. P-type has majority carriers that are holes, and n-type has majority carriers that are electron. And when you put the two together, it forms a built-in electric field, and that electric field is responsible for separating charge. So what you can see about this process is that electrons that have, or photons I should say, that have an energy greater than the band gap are able to promote an electron from the valence band to the conduction band. However, if the energy of the photon is less than the band gap, basically you can't have any absorption, and therefore the semiconductor is transparent. Another issue is that when you create an electron hole pair, it has a certain excess energy above the band gap, and what typically happens is that the electron or the hole quickly loses energy and relaxes to the band edge. It goes to the lowest energy state, and so you lose all the extra energy of the photon basically into producing heat. So these are two losses, and I'll talk about how these lead to basically the maximum conversion efficiency of a solar cell. So that's the basics of how electron hole separation occurs and how you get a photocurrent. What's shown in the other pictures are implementations of a solar cell. So this over on the right basically illustrates or shows the top view of a commercial silicon solar cell. And what you can see is it looks kind of bluish in color, and that's because there's an anti-reflection coating that helps to reduce the reflection off the surface. And you can see a metal grid line. And the purpose of that you can see in this picture. This is a cross-sectional view of a p-n junction solar cell. It corresponds to the picture that I showed here energetically. But what it shows is the structure. It shows that at the top, basically, well, let's start at the bottom. Basically it starts with a silicon wafer, which is about 150 to 200 microns thick, which is doped p-type. And on top of that then is grown or diffused n-type material to form the p-n junction. So what's shown here is the n side, which is this side over here, and here's the p side, which corresponds to this side over here. And so light is absorbed, and the light is absorbed at different depths because there's a quantity called the absorption coefficient that determines how far light goes in before it's absorbed. And blue light is absorbed very quickly, green light not so quickly, and red light has the furthest penetration. So different colors of light go to different depths within the silicon material. And then they basically, once they're created, the electron and the hole have to diffuse. The electron diffuses up to this, to the edge of what's called the space charge region, which was this region, and is swept across and becomes the photocurrent. Likewise, a hole that's created here is swept across and becomes the photocurrent due to holes. So you can see that you have various colors being absorbed at different depths, and that plays an important role in the design of the solar cell. And on the top and the bottom, you have to make a contact. You have to get electricity out somehow. So you have basically what's called an ohmic contact, which makes an ideal contact to the semiconductor and extracts charge out the back. And then you have metal grid lines. These little black areas represent grid lines. They correspond to the same lines that were shown up here. And that's how you extract charge from the surface. And this plays a parasitic effect because wherever you have a grid line, it blocks light coming in. So you have to minimize this area of the grid. So typically this grid is designed so that there's less than 5%, 10 to 5% of reflection. Otherwise you lose efficiency of the solar cell. And then the blue just represents the anti-reflection coating. So finally, what's shown on the left is what's called the current voltage characteristic of the solar cell. This is basically a plot of the energy put out by the solar cell as a function of the load. You can think of this as being that this solar cell is connected to some kind of load, which I designate with this sign, which represents a resistor. And when current flows through this, there's a voltage, and that voltage feeds back onto the cell and creates a dark current that opposes the photocurrent. So what's shown here basically is the current voltage characteristic of the solar cell in the dark, which is this curve here. And then you see the curve in the light. So the curve in the dark, this represents the dark current that flows due to this voltage here. And the photocurrent basically is the current that's flowing in the opposite direction due to the light generation. And so you can basically just shift this curve down by the amount of light generation, and this is the current voltage characteristic of the photocell. And there's 3 points of interest on this that I'll refer to as we go further into the slides. One is what's called the short circuit current, and that's basically the net photocurrent that's produced by this process I showed here, this photogeneration process. So this is the current entirely due to the photons that are absorbed and get transferred across the junction, and this represents then the maximum current that you can achieve in the cell. The other limit is what's called the open circuit voltage, and that is if you basically open the circuit, if you get rid of the resistive load, no current can flow. The dark current basically is equal to the light current, and you have zero current flowing. So this open circuit voltage is the maximum voltage that the cell can produce and generate power. But both of these cases, the short circuit current and the open circuit voltage, neither of these can produce power because power is the product of voltage times current. And so there's a maximum power point, which is shown by B here, which the cell has to operate at to produce the maximum power. So that's where useful work is done when you operate at this point. And there are various schemes when you produce cells and modules to make sure that the module or the cell always works at that maximum power point, which I won't go into detail today about. Anyway, that was a brief overview of how a solar cell operates. I'll move a little bit faster now in the rest of the material. This is a sort of snapshot of different solar cell technologies. And so what's shown is the periodic table. And in the periodic table, basically column 4, these correspond to typical elemental semiconductors. What characterizes a semiconductor typically is that a semiconductor has an average of 4 valence electrons per atom. So silicon, germanium, because they're in column 4, have 4 valence electrons, and these are available for bonding, and they form covalent bonds, and this is responsible for the crystal structure. So silicon, germanium are semiconductors, and then other materials, 3,5 compounds, between column 3 and column 5, or column 2 and column 6, when they're mixed together, they form basically a compound with 2 different elements. 3,5 materials have an average of 4 valence electrons because one's column 3 and one's column 5. So gallium arsenide, for example, indium phosphide are typical 3,5 compound materials. And cadmium telluride, for example, is a very common thin film material used, 2,6 compound in thin film solar cells. So there's different generations of technology, and some people don't like this nomenclature, but it's stuck around, and what we call first generation basically is the most commercially viable technology, which is silicon single and polycrystalline solar cell technology, which is today, presently, probably 95% of the market. There's other first generation technologies. These are all based on sort of semiconductor wafers. And so the technology is to grow silicon, basically large crystals of single crystal silicon, and cut them up into wafers. And on those wafers, we make the solar cells. The same is true for 3,5 solar cells, gallium arsenide, indium phosphide. These operate basically the same and have been used, for example, very often in spacecraft applications, which was one of the first applications actually of photovoltaic technology, and that is in satellite technology to replace heavy lead-acid batteries. Second generation technology is often referred to in terms of thin film technology. And second generation technology is different than first generation technology in the sense that thin film technology uses basically deposited very thin layers of material onto cheap substrates like glass, steel, polymers, etc. Thin film technologies include, for example, amorphous silicon, which can be basically evaporated onto glass and form solar cells. The largest commercial technology is probably that due to cadmium telluride, It's actually cadmium telluride combined with cadmium sulfide. And cadmium telluride solar cells are basically the largest thin film technology today and used for a lot of very large utility scale projects. I'm going to focus today more on what we call third generation. And third generation are basically technologies that seek to go to very high efficiencies in terms of solar cells. And I'll talk about those limits in a minute, but third generation technologies include what's called multi-junction or tandem solar cells, which is actually a commercial technology which is available today and which achieves efficiencies that are much higher than conventional silicon solar cells. Another topic that's become very important lately is that of perovskite solar cells, which have received a lot of attention. I won't talk about those today, but perovskite solar cells have achieved remarkable efficiency improvements over the last few years. Dye-sensitized solar cells, basically perovskite solar cells are similar to dye-sensitized solar cells, and this is why they're important. And then I'll talk about advanced concepts today, and that's where nanotechnology plays a role. Advanced concepts are concepts that allow us to achieve the maximum conversion efficiencies that approach basically the maximum thermodynamic conversion efficiency that's possible. While I'm discussing this, I just want to talk about also a center that's located at Arizona State University. That is the NSF DOE-funded Quantum Energy for Sustainable Solar Technology Engineering Research Center, or QUEST. And this is a large multi-university center headquartered at Arizona State University, the largest center for photovoltaics funded by the National Science Foundation. And it's basically a collaboration between universities and industry. And its focus is on meeting what's called the terawatt challenge. And by the terawatt challenge, what we mean is, can photovoltaics be scaled up to a high enough level to basically produce terawatts of electricity? We use the word terawatt because terawatts of electricity in terms of power are basically the power requirements for example, the powering the United States and the world. It's measured in terawatts, the United States being something on the order of 4 to 5 terawatts peak, the world being scaled above that. But basically, the sort of scale of energy that's necessary for meeting the current energy needs is measured in terawatts of peak power. And that terawatts, in comparison to where solar cell is quite large, because solar energy technologies in general, and including wind and other alternative energy technologies, are really only 5 to 10% of the total energy of the current world right now. Most of it's based on fossil fuels, with the commensurate problems in terms of climate change and other problems associated with large-scale use of fossil fuels. So terawatt challenge means taking the current power production of technologies like photovoltaics from the gigawatt scale to the terawatt scale. And so a lot of focus of this is on technologies, for instance, that are scalable in terms of materials, in terms of abundance of materials, and of course in terms of manufacturing. So this contains 3 levels, as typical of these National Science Foundation centers. And what I'm going to talk about today are sort of the enabling technologies that are at the bottom of this. In other words, the fundamental technologies that are responsible for new innovations in solar cells and trying to advance solar cells to keep improving the performance and lowering the cost. This is a plot of solar cell efficiencies just to illustrate sort of the trends over several decades. This starts at 1975 and goes to 2015. So it covers at least 3 decades. And what is shown on this is, or what you can see is that solar cell efficiencies have not increased dramatically. It's sort of a monotonic increase with time. As you can see, all technologies kind of go up, some saturate, others go to higher efficiencies. These higher efficiencies up here I'll talk about are associated with the multi-junction solar cells or tandem solar cells. Silicon technology is down here, and you can see that there's new technologies that actually have a very steep curve. These include the perovskite solar cells, some organic solar cells, thin film solar cells, the cadmium telluride. So there's a number of technologies, as you can see, in recent years that have changed the slope of this increase in efficiency over decades, and that's very promising for the future of photovoltaic technology. And I should mention that at the same time, there's been a cost reduction that's also been going down at a much faster rate, and that cost reduction also is very favorable in terms of the future of photovoltaic technology. So I want to talk about now are basically what are the limits of the conversion efficiency, what limits basically the conversion efficiency of a photovoltaic device, and what's the maximum conversion efficiency that we can have. What's shown here basically is a schematic of the solar energy spectrum. The solar energy spectrum, the actual solar energy spectrum is of course not this smooth. This is more representative of the solar energy spectrum in outer space. Basically, it's represented by what's called a black body curve, and that is that as a function of wavelength, there's a peak in this, which is a function of the temperature of the source. And this characteristic shape then, for each different temperature, basically the peak shifts over to this direction as the temperature goes down. So the sun is basically, can be considered a black body source with a temperature around 6,000 degrees centigrade. And the characteristic black body curve looks something like this. So this line here represents the band gap of a solar cell. As I said, that's the fundamental quantity that determines the performance. And the reason for that is that all of the photons, so this represents the distribution, the spectral intensity represents the amount of energy in each part of the spectrum. And the spectrum, what we mean by spectrum is then the spread in wavelengths. And as you can see, below the band gap, as we said, no photons are absorbed. So already this red portion of the spectrum is lost. Okay, so you lose all the photons below the band gap. Now, as I mentioned before, and if you look at the curve on the right, for photons that have energy greater than the band gap, the excess energy of the carriers is quickly lost due to thermal processes, and you only collect energy at the band gap, and actually somewhat less than the band gap. It's a small fraction below the band gap that you actually can collect energy. In other words, the open circuit voltage is determined by the band gap minus some fixed amount. So there's two losses then. One is the loss of the photons below the band gap. The second is the loss of the excess energy of the photon above the band gap. And so you only really utilize photons at the energy of the band gap. And because of this then, basically, an analysis was done using a process called detailed balance, which is an ideal sort of thermodynamic analysis of the maximum efficiency of a solar cell with a single band gap under what's called one sun intensity. In particular, AM 1.5 refers to the spectrum of light that's seen at the Earth's surface at a certain latitude. That latitude is approximately the latitude of Denver in this case. In any case, this analysis showed that the maximum efficiency for a single gap is 33.7%. This just shows the solar energy, actual solar energy spectrum. The yellow is the spectrum in outer space, and you can see that it follows pretty closely to the black body radiation curve in an ideal sense. The spectrum at the Earth's surface, however, is quite different, and that's because of things like greenhouse gases, which absorb some of the spectrum. Water absorbs some of the spectrum, carbon dioxide, ozone. So there's different molecular species in the atmosphere that absorb particular parts of the solar spectrum preferentially. That's what causes these dips. And there's an overall trend of reducing intensity, which is associated with what's called Rayleigh scattering. That is simply the scattering of light at short wavelengths, which is responsible essentially for the light, for the sky being blue. Okay, that's the part of the solar spectrum that's scattered and can be collected by the solar cells, but not directly. This is another picture of the Shockley-Queisser analysis, and basically the Shockley-Queisser analysis is shown by this black curve down below. This shows the basically maximum conversion efficiency of sunlight to electricity as a function of the band gap of the material. So as you can see, it starts off at small band gaps, it starts off low, it increases and reaches a maximum about between 1.1 and 1.4 electron volts, and then it goes down again. And that's because of these two processes that I mentioned. That is that for small band gaps, most of the photons are absorbed, but most of the energy is lost by this relaxation back to the band edges, thermal loss. For large band gap materials, most of the photons aren't absorbed, and so you lose basically the photons that are below the band gap. So in this trade-off, there's an optimum, and the optimum actually fortuitously occurs around the band gap of silicon and gallium arsenide. And so in this range, turns out that silicon not only is an earth-abundant material, but it turns out to be very favorable for reaching the maximum, what we call Shockley-Queisser efficiency. However, this efficiency, this 33%, is much less than the maximum thermodynamic conversion efficiency based on pure thermodynamics of sunlight to usable energy, in particular electricity. That energy is closer to 86%, which is up here. And you can see that then there's a large difference between where solar cells are in terms of 33% maximum efficiency and where they could potentially be in terms of thermodynamic efficiency of 86%. And that's part of what these advanced concept or third concept types of cells are trying to address. So how can you circumvent the Shockley-Queisser limit? Okay, so the Shockley-Queisser limit is based on a number of different assumptions about the nature of the photovoltaic conversion process, which I'll just briefly discuss. So first of all, one assumption from that was made by Shockley and Queisser is that the solar spectrum is basically the solar spectrum. That is, it's a broadband source. And so part of the problem is that the solar spectrum covers a wide range of frequencies or wavelengths. And therefore, the optimum band gap for a single band gap is not a good fit to the entire spectrum. So if you could shrink the spectrum, if you could make the solar energy spectrum much narrower, if you could make it a single wavelength, it'd be, of course, very boring here. But if you could make the solar spectrum a single wavelength, then the efficiency would go much higher, closer to the thermodynamic limit. Another issue is that is the assumption that you have one photon and that creates one electron hole pair, and that only occurs when the energy of the photon is greater than the band gap. But there's multiple paths to also create electron hole pairs, and that is you can have a high energy photon that creates an electron hole pair, but before that electron hole pair can relax, the high energy electron can actually create a second electron hole pair. So in that way, you can get two electron hole pairs for a single photon and circumvent the Shockley-Queisser limit. You can also have two photon absorption, which would allow subband gap photons to be absorbed, two of them at a time, to kick up an electron from the valence to the conduction band. That would also circumvent the Shockley-Queisser assumption. Another is that you have a single band gap, okay? So if you could envision a solar cell that had multiple band gaps, you could fit different portions of the spectrum to different band gap materials. And that's exactly what's done in multi-junction devices. If you have multi-band gap materials, basically then what you can do is reach the thermodynamic limit. You can reach a conversion efficiency of 86% if you were able to put together an infinite number of band gaps. And we'll talk about a little bit about how close you can get in reality. You can also make materials not only multi-junction materials, but you can introduce materials or have materials that have multiple levels within them. And that material then acts like a multi-level material, multi-junction material, and will produce electricity at a higher efficiency than a single gap material. There's the assumption of basically collecting the electrons at the band edge, in other words, at the temperature of the crystal. But actually, if you could harness the energy of the electrons before they have time to lose their energy to heat, you could also have a high efficiency cell. And there's ideas in which we can, if one could keep the energy, the heat energy and the excess energy of the electron within the cell and extract the electrons at high energy rather than at the band edge, then you could also exceed the Shockley-Queisser limit. And this is the so-called concept of hot electron solar cells. And finally, if you could make a hybrid system in which basically you take part of the spectrum and utilize that for doing photovoltaics, but the photons below the band gap are harvested in a thermal system and produce thermal energy, you can also exceed the Shockley-Queisser limit in such hybrid systems. In other words, instead of wasting the photons below the band gap, you do useful work in turning that energy into heat and harvesting that heat either for electricity or for some other application like solar hot water heating. Anyway, these are ways of overcoming the Shockley-Queisser limit, and we'll talk a little bit more in detail about that. But just to mention, as I said, tandem solar cells or multi-junction solar cells are basically solar cells that have achieved the Shockley-Queisser limit. and have the highest efficiencies to date. These multi-junction cells, tandem cells, are basically made by stacking cells on top of each other in a fashion such that the top cell has the widest band gap, the next cell has the next highest band gap, and the lowest cell has the smallest band gap. And so essentially, as the light comes through, you harvest it in each of the cells. You take off the high energy photons in the top cell, the medium energy photons in the second cell, and the bottom cell harvests the rest of the photons. This is a technique or a technology that's used now commercially in extraterrestrial applications, because in extraterrestrial applications, in other words, in satellite and spacecraft, it's not the cost of the cell that's important, it's the weight of the cell. And therefore, reducing the weight is a premium in terms of the price, and therefore you can sustain a higher price for the solar cell, which these cells are quite costly in comparison to, for example, conventional silicon solar cells. So in that application then, it's commercially viable. For terrestrial applications, the strategy that's being used is to use multi-junction cells in concentrating photovoltaic systems, or CPV for short. This basically illustrates a CPV system. What's shown here is basically a mirror which is concentrating light over a much broader area onto a small array, which is basically shown here, of multi-junction solar cells. And so you have you have costly but high efficiency cells in a small area, and then you concentrate light from a much larger area. So this way you push the cost of the solar cell from the cell itself to the system. So the cost now is in the mirrors and the tracking technology that's necessary to track the sun, because in order to focus light from the sun, you have to track it very accurately, in fact. So this creates different kinds of trade-offs in terms of the costs and benefits. This is just an illustration of what's called a three-junction tandem solar cell. And as I said, this one is composed of three materials, gallium indium phosphide, gallium arsenide, and germanium. Germanium has a band gap of about 0.67, gallium arsenide 1.43, and gallium indium phosphide 1.82. Now, these materials are in particular chosen because they are lattice matched. And what I mean by lattice match is they have the same crystal structure and they have exactly the same spacing between the atoms. That's called lattice matching. And that's important because you're going to grow this basically in one shot in a vacuum system. And as you deposit it, if they're not lattice matched, you have thermal mismatch, and you have, well, more importantly, is that you have strain that builds up. And the strain eventually overcomes the crystal structure and causes defects to form and degrades the performance. But as I discussed, the wide band gap cell is on the top. Light is coming in from the top. Part of it's harvested in the gallium indium phosphide layer. Part of it's harvested, the next part harvests the photons that are left in the gallium arsenide layer. And then finally, the rest of the photons are harvested in the germanium layer. And so in this way, with this three-junction solar cell, you can achieve efficiencies that are substantially higher than the Shockley-Queisser limit. This is the plot of efficiency versus time, and these, the upper corner here basically represent the multi-junction cells that I've been talking about. Three-junction cells, and now more recently four-junction cells that have achieved conversion efficiencies under concentration over 46%. So that's sort of the current world record today in terms of efficiency. And as I said, you can keep increasing the efficiency theoretically if you keep adding more junctions, but these constraints in terms of the materials and lattice matching and a lot of other considerations so far make it difficult to go above 46%. We anticipate that we'll reach over 50% within a few years, and there's a lot of research in this area, but today commercially, the applications are limited, as I said, to extraterrestrial applications for spacecraft, and there's a small but growing concentrating photovoltaic industry as well. So now I want to turn to the main topic of this lecture, which has to do with third-generation concepts. And third-generation concepts are concepts which to date have not achieved efficiencies higher than the normal solar cell efficiencies, but are pathways towards reaching those. and are being pursued by various groups around the world. So what are shown here are three sort of pathways to that, and then a fourth one, which I'll talk about, which has to do with light management. So the first one is what I call multi-exciton generation, or sometimes multi-electron generation, or impact ionization. The idea simply is that you have an absorber, and it can be a solar cell material, or more frequently, it's what's called a quantum dot, which is a nanostructured type of material, which I'll talk about. And when you excite an electron from the valence band to the conduction band, it has enough energy in this level to fall down and create a second electron hole pair. So this is a process that's often referred to as impact ionization or inverse Auger recombination. And it requires then that this energy between this level and this level be twice the band gap. So once it's twice the band gap, you can create 2 electron hole pairs. If it's 3 times the band gap, you can create 3 electron hole pairs. And so in this way, you have a quantum efficiency that's greater than 1, and the overall conversion efficiency can be greater than 33%. What's shown on the right is what's called an intermediate band solar cell. This is architecturally very similar to a tandem solar cell, except that the actual multi-junction is all contained within one material. That is, that there's an intermediate level, shown here by labeled IB, and this is sort of a place that an electron can park itself when it's excited. So you have a long wavelength photon, can excite this electron from the valence band to this intermediate level, and then a second photon can come in and excite it from that level to the conduction band. So there's a host material which has a band gap EG, as shown over here. Okay, that's wider than these intermediate levels. And so basically the idea is that you can produce a voltage that corresponds to this wide band gap, E sub G, but you're harvesting electrons at a photon energy smaller than the band gap by this 2-step process. So it's kind of like a 2-photon absorption process. But thermodynamically, or at least from an analysis point of view, using detailed balance, it resembles quite a bit the efficiency gain that you get from a tandem solar cell. In other words, it introduces extra levels and therefore circumvents the single gap limit that you have in the Shockley-Queisser analysis. And finally, what's shown down here is the schematic of a hot carrier solar cell. And the hot carrier solar cell basically consists of a material with a band gap that's relatively small, and is referred to the absorber as an absorber. And this material basically is a material that has a very small energy relaxation. And how you realize that is of course, the big challenge. But if you could shut down, or if you could slow down the rate of energy loss of electrons to thermal processes, and keep that energy within the system, you create what are called hot electrons, which means that the average temperature of the electrons as measured by their kinetic energy is much higher than the temperature of the crystal lattice that's the absorber itself. And in order to implement this scheme in a useful way, you have to introduce what are called energy selective contacts. There's one contact made to the electron gas, there's another one made to the whole gas, and the energy of this energy selective contact is above that of the energy gap of the absorber. So electrons are harvested out of the contacts at this energy, and therefore the voltage at which you produce electricity is due to the difference in energy of these energy selective contacts, but you harvest electrons at this much smaller gap energy. And this scheme of a hot energy solar cell also can reach, theoretically, the thermodynamic maximum efficiency conversion on the order of 86%. Another important issue is that of what we call light management. And that is that how do we get electrons, how do we absorb more of the light that's coming in and not lose it, for example, due to transparency, etc. This is particularly important for materials like silicon, because material like silicon has a relatively low absorption, and therefore a lot of the light, particularly the long wavelength light, is not absorbed in the silicon and is lost. And in particular, theoretically, the performance of silicon solar cells would become better if we could make them thinner and thinner from the point of view of their voltage. And you would use less material, which would make the cost much cheaper. And so there's a large push to going to thinner and thinner materials, and that requires then absorbing more and more of the light and redirecting the light in a way to absorb most of the photons. So there's schemes such as nanophotonic crystals and nanoplasmonics that are being researched that try to improve this. So let me talk about nanotechnology briefly, and nanotechnology basically refers to technology at the nanometer scale, nanometer being 10 to the minus 9th meters. And generally we talk about something being nanotechnology when the characteristic dimensions are smaller than, say, 100 nanometers, which is sort of an arbitrary cutoff, but by way of comparison, basically now your computer technology is a nanotechnology because the characteristic dimensions of the transistors made by companies like Intel, the critical dimensions are now less than 50 nanometers, more like 30 nanometers. And so basically the microelectronics industry and the computer chip industry is basically a nanotechnology industry. So nanotechnology is not something that is pie in the sky, it's a major component of a multi-billion-dollar industry. These are some nanotechnology components, and basically nanotechnology components include two-dimensional structures, one-dimensional structures, and zero-dimensional structures in terms of what I call confinement, or their shape. You have sort of nanowire types of structures, and what I mean by nanowires is that the structures such as this structure and this structure are essentially one-dimensional in nature. That is, the atoms arrange themselves along a wire. So basically current moves along the wire. This is an example of what's called self-assembled semiconductor nanowire, whereas this is what's called a carbon nanotube, which is basically a sheet of carbon atoms that's wrapped around on itself and forms a stable structure which conducts electricity. It can be conducting, it can be metal, it can act as a semiconductor, it can act as an insulator depending on how we wrap around these sheets, which is quite interesting. It's an example of what we call a fullerene type of material. You could make molecular wires by taking atoms and pulling them apart and creating molecular chains. So there's different ways of making these sort of quasi-one-dimensional systems, which are essentially nanowires. And increasingly, the transistors that form the microelectronics industry are also becoming sort of nanowire shape and structure. You can have quantum wells, as shown here, and that's older technology. And it's basically realized, so what's shown here is basically a schematic of what's called a superlattice or a multi-quantum well system. And this is realized by taking a material with a wide band gap and sandwiching it with a narrow gap material, and then growing another wide band gap material, narrow gap, wide band gap, narrow, et cetera, et cetera. You can do this with a process called molecular beam epitaxy, and molecular beam epitaxy essentially is a layer by layer growth technique in which you grow atoms one by one. You grow layers one by one on the surface of a semiconductor, and so you can control atomic layer by atomic layer the thickness of the material. And so you can alter or vary or create new effective band gaps by the spacing and the width of these wells and so forth. And these quantum wells and superlattices play, for instance, an important role in some of the multi-junction technologies that are currently of interest. Finally, you can make zero-dimensional systems by making what are called quantum dots or nanoparticles, nanocrystals. There's a variety of different names, but they essentially have to do with what most commonly, or what the analogy is, an artificial molecule. What's shown here is a nanocrystal of, I'm not sure what material, probably this could be a silicon nanoparticle embedded in silicon dioxide. But in any case, what you can see, this is an electron micrograph image, a lattice image using high resolution electron microscopy. And in high resolution electron microscopy, you're actually looking at either individual atoms or the molecular basis pair of the underlying crystal. And so you can see that there's a spherical object which has a regular crystal structure which forms a stable structure called a nanoparticle. So these can be grown in solution, they can be synthesized in solution, or they can be grown, as shown down here, during epitaxial growth, the same process that's used to grow this, but if you grow it under high strain conditions instead of the layers growing layer by layer, they clump up and form basically pyramids. And these pyramids are stable, and they actually form with a distribution that's fairly uniform around the crystal. And these pyramids then form quantum dots or nanoparticles that have basically zero-dimensional or molecular type of energy states. So these are sort of the tool bag of nanotechnology that we have available to us and what we try to utilize. The advantages of nanotechnology are that some of the things that make them advantageous are also a disadvantage, particularly for photovoltaic applications. And what I mean by that is that one of the things that changes the properties of nanostructured systems compared to bulk materials is that they have a large surface to volume ratio. That is, surfaces play a much larger role than do the bulk when you go to nanostructures. And these surfaces are responsible for example, making different catalytic properties. So you can change the catalytic properties of materials, you can change the chemical bonding properties. Obviously, the electronic states change, and so there's a lot of tuning that you can do with the surface. On the other hand, surfaces are points at which recombination can occur. And recombination is the process in which an electron and hole that have been created by light, instead of moving apart and being collected, fall back down and basically recombine, either giving off light or heat. So anytime a particle recombines, it basically means you've lost it to photocurrent. And since you've lost it, that reduces the efficiency. It also increases the dark current, and as you increase the dark current, recombination then degrades the voltage, and so it has two negative effects. One is reducing the open circuit voltage and the short circuit current, and hence the power. So the problem then in nanostructures is that they have a high surface to volume ratio, and therefore that means that surfaces can dominate and dominate in a negative way. And so therefore passivation, which is passivation is the process of basically mitigating the effect of these dangling bonds and broken bonds on the surface, tying them up with some other material like organic material or an oxide. Passivation plays a much more important role in terms of using nanotechnology in solar cells than in other technologies. I want to talk a little bit about research that we're involved with at Arizona State University, in particular my own group, in terms of modeling of third-generation photovoltaic devices. And basically, modeling and simulation of nanoscale type of solar cells is inherently multi-physics type of problem. And the reason for that is that you have a huge difference in time scales and a huge difference in distance scales in terms of the overall architecture of the solar cell. We have basically, at very short time scales, we have the processes that are responsible for energy relaxation. That is, the emission of quanta of heat called phonons by the electrons. This occurs at a picosecond time scale, or 10 to the minus 12 seconds. On the other hand, recombination processes, that is, the electron and the hole actually recombining before being collected, these processes occur on time scales that range from 10 to the minus 9th seconds to milliseconds, 10 to the minus 3rd seconds. So basically, you have over 10 orders of magnitude difference of time scales of the different events that are occurring. Okay, so this is one problem in terms of simulation, is dealing with large temporal scales. And then, of course, you have different distance scales. So you may have a nanostructured cell in which transport within the nanostructure occurs over a few nanometers of dimension, but the rest of the cell is several microns thick. And so you have distance scales that are tens of microns, even hundreds of microns in silicon cells, compared to a few nanometers. And so therefore you have to resolve both very short length scales and very long time scales. And so basically the approach that one has to do is sort of illustrated in this chart, and that is that you have things with short time and spatial dimensions at this corner, and things at long time and large spatial scales at the other. And this basically corresponds down at this end to sort of the molecular scale, and at this end to the system scale for devices. And so basically the typical approach that's used is to use multi-scale modeling, in which high fidelity types of physics models are used at this level, and then the information that you get from modeling is passed to the next level. That information is used, for example, for let's say electronic structure, doing first principles electronic structure. to get to electronic states and the vibrational states of the material. That's fed into a simulation or a suite of simulation tools that do simulation of transport, for example. This could be transport at short time scales, for example. And then transport at longer time scales, again, goes through a process in which you go from, say, a molecular picture or atomic picture of transport to a continuum picture of transport that is more analogous to water flow. And then finally, going from continuum to full systems basically means abstracting everything in terms of what we call lumped parameters, that is behavioral models that take the information from this modeling at these three levels and combines it into a nonlinear set of differential equations that allows us to model the performance of a system as a whole. So one can think of for example, a system of solar cells, a solar module, as being this level, whereas the processes that occur right at the junction and the separation of the electrons being down at this level. So this sort of illustrates the approach that one has to take. It's not perfect. There's information lost when you go from level to level, but it's very difficult to start at this level and be able to simulate a whole system. It would be computationally impossible today with the computers we have. This is just another illustration specifically about how we do modeling and simulation of photovoltaic devices or electronic devices. And that is, there's several components. One is that we have information about the electronic structure of the material, the vibrational structure of the material, and that has to be fed basically into some kinetic model that describes transport of charge or transport of heat. So there's several different quantities that are transported. The main ones, the three main ones being transport of charge, transport of heat, and transport of light, of course. Transport of light, as though, corresponds to the solutions of the electromagnetic fields. So at each of these levels, there are different techniques that we utilize and other groups utilize, and these are just acronyms for things like empirical pseudopotential, tight binding, our empirical methods of solving electronic structure. Density functional theory is ab initio techniques for solving the electronic structure. VSM, Keating, these refer to models for the lattice vibrational motion, that is the vibration of the crystal that's responsible for heat transport. And these ingredients then are coupled together and used at various levels and fed into the kinetic equations. What drives charge, however, and this is what makes it a very coupled problem, is that charge moves in the presence of electric fields. But electric fields basically are derived from the motion of charge, so it's a self-consistent problem. That is that the source of electromagnetic fields is either static charge or the motion of charge in terms of magnetic fields. However, the motion of charge is due to the force acting on them by electric fields, also by chemical gradients and things like that. So there's various different techniques for solving for electromagnetic fields. Depending on the degree of accuracy, if the electric fields are not too high, you can use what are called quasi-static approximations and solve for the electromagnetic fields using multigrid or successive over-relaxation solutions of Poisson's equation, which is basically the quasi-static solution under non-time varying situations. At for high frequencies, one has to deal with finite difference time domain, a method of moments methods, etc., frequency domain, time domain methods of solving the electromagnetic fields. And we need full wave solutions when we talk about when we talk about the optical field that's associated with light and the interaction of that with the electric and vibrational motion of the crystal. So finally, there's the transport kernel, and transport basically is associated with the motion of charge and how we describe the motion of charge. Fundamentally, that it's described by what's called a kinetic equation approach, and that kinetic equation can be fully quantum mechanical, which is what the non-equilibrium Green's function method involves. Or it can be semi-classical, based on looking at the motion of particles and describing the motion of particles under the electric and magnetic fields that are present. Monte Carlo basically is at that level. Or we can treat and Monte Carlo corresponds to the solution of what's called the Boltzmann transport equation, which is basically a statistical description of the motion of charge in terms of a distribution function and the equation of motion for a distribution function. If you take moments of the Boltzmann transport equation, you come up with a description which is called hydrodynamic or drift diffusion. And these are continuum representations of transport in terms of treating motion of charge as motion of a fluid, basically. So it's a continuum way of treating charge transport, which is more approximate than, say, microscopic approaches based on Monte Carlo or NEGF, but have the advantage of being able to basically scale different length scales and time scales in a fairly efficient manner. So we use this at a higher level. We use the Monte Carlo and NEGF at the microscopic level. And then you have to basically go between the different levels in terms of levels of approximation. So this is sort of a scheme of self-consistent modeling, and I'll talk about some applications of this in the rest of the talk. We use, in particular, our group uses a lot Monte Carlo simulation. And Monte Carlo simulation is simply simulation of basically classical charges using statistical methods, meaning that we use the random number generator on the computer to simulate the random collision events that particles have. And between collisions, the particles are assumed to accelerate classically according to the force that's acting on them, say, due to an electric or a magnetic field. So the statistical part has to do with random events. And so you use the random number generator on the computer, and you scatter particles based on a quantum mechanical description of the scattering probability. So you use quantum mechanics in order to calculate what's called the scattering cross-section or the scattering rate, and the probability of scattering in a certain direction. And you put that together in a computer simulation in which you simulate an ensemble, where the word ensemble comes from. In other words, you simulate tens or hundreds of thousands or even millions of particles at the same time, using the same algorithm for each particle, which basically accounts for all the possible mechanisms that the electron or hole can scatter from as it moves through the crystal. And those include, basically, these are scattering due to phonons. Phonons. And phonons are quanta of thermal energy. They're the quanta of vibrational motion, just like a photon is a quanta of a electromagnetic radiation and is described as a particle. So you have wave-particle duality in electromagnetics. You also have wave-particle duality in the motion of the crystal and the vibrational motion of the crystal. And those quanta of the crystal are called phonons. And we describe the interaction between electrons and phonons in terms of particle interactions. And that fits very well into this framework, this particle framework of Monte Carlo. So there's different kinds of phonons that interact. The electrons can scatter amongst themselves. They can scatter with the holes. They can scatter in a bulk material, or they can scatter in a quantum confined system. So a lot of what I talk about has to do with nanostructured systems such as quantum wells and nanowires, in which we calculate the scattering rates. This is a comparison of the bulk scattering rate in blue, and the green scattering rate is that of a self-assembled nanowire of indium arsenide, just to illustrate that these scattering rates can be calculated either in bulk or for nanostructured systems, which is what we do. So there's other things that can be affected, but in particular, we try to include the full band structure into these calculations, and that is that we use an electronic structure calculation in order to get the electronic structure, and then we use that as the states between which electrons scatter in a full band picture of transport in the material. We also consider basically the motion of phonons, and so you can treat phonons also within the framework of Monte Carlo. You can treat the particles, the phonons themselves, within an ensemble Monte Carlo approach, and you can keep track of their population, and you can account for the fact that the phonons may move out of equilibrium just like the electrons can, and that becomes important in some concepts like hot carrier solar cells, which I'll talk about. So the first topic I want to talk about is light trapping. And light trapping, as I mentioned, is important, particularly when we go to thinner and thinner materials. So we want to save material, and you need to absorb as much light as possible. So the problem with a thin material is that if you have a certain thickness of material and light is incident on it, basically it goes through the material. It may reflect off the back, but it basically goes through a short distance, which is the thickness of the material, and basically goes out the other side. So light trapping in a classical sense, I mean thinking of light as rays, is enabled by making, as pictured here, rough interfaces. So if you have rough surfaces optically, light that comes in is basically scattered randomly by the facets and roughness of the surface. And once it changes direction, it moves laterally in the material, and its path length is enhanced. And its path length enhancement means that it travels longer distance and therefore has more chance of being absorbed. And so light trapping is used now practically in commercial silicon solar cells in order to increase the capture of photons as you make silicon cells thinner and thinner and reduce their cost. You're limited in terms of this approach, in terms of light trapping, to what's called the so-called classical light trapping limit. And that classical light trapping limit is basically that the effective path length, if this is a width W, the maximum enhancement of the path length that you can get from a totally random scattering from the surface is 4 times the index of refraction of the material itself and the width of the material. So this, basically the enhancement is 4n squared over the normal width W. And n for a semiconductor can be on the order of 3 to 4, so therefore the enhancement can be quite large. It can be, over a factor of 50. Okay, but can you go beyond that? And so one of the things that is being looked at using nanotechnology is whether or not you can actually go beyond the classical light trapping limit, this 4n squared limit, and actually have a longer path length. And that means that you have to go beyond ray optics. You have to go to basically full wave optics, in which diffraction becomes important, and you need to look at structures that have characteristic dimensions and spacings that are much less than, say, the wavelength of the light. So what's shown here on the left is work that was done by Harry Atwater's group at Caltech, and that was looking at enhancement of light trapping due to forming a forest or an array of nanowires. And these nanowires basically act as, you can think of it as acting as little antennas. They actually form, in one sense, a photonic band gap structure, which I'll talk about. But in any case, these forest of nanowires basically capture the light, traps the light inside, and leads to more absorption. And so this picture here basically is illustrating, the purple represents the enhancements you have from classical light trapping due to having a rough surface. The extra red shown here is an enhancement that they measured which goes beyond the classical light trapping limit, demonstrating that a nanostructured type of surface can give you an increased path length or trapping that's beyond the classical limit. This can also be realized using nanoplasmonic systems, in which an array of metallic scatterers leads to the formation of surface polariton modes, so-called modes that form at the parallel to the surface and also lead to light trapping. So there's also a lot of work on the nanoplasmonic approaches. Photonic band gap structure materials, I don't want to go too much into detail of this other than to say that if you make a periodic array of scatterers optically, it plays the same role as a periodic array of atoms does in creating a band structure and creating a band gap. That is that in terms of the wavelength or momentum of electrons, there's gaps that are opened up in the spectrum of a crystal in terms of its electronic states that lead to the formation of a band gap. And so this difference between here and here is what we call the band gap of the semiconductor. And this is a different kind of picture than I showed before. This is a picture in momentum space of the band gap. Similarly, if you make an array of scatterers, and I've shown some examples down here in terms of nanowires, holes, force of etched holes, so there's many different ways of making such structures. And normally the optical dispersion is a linear relationship, but because of the scattering, the periodic scattering, you open gaps in the dispersion of light, and you have basically a bending over and new modes that start up here. And there's basically gaps that are opened, and these gaps correspond to what are called photonic band gaps, in which you have no propagation of light. And so you can play with this spectrum, and you can play with the photonic band gap structure itself and try to engineer this in order to capture more light into the semiconductor. This is some work ongoing at Arizona State University, and the picture on the left corresponds to basically a forest of a nanowire array that was formed by what's called nanosphere lithography. And I don't have time to describe that, but essentially an array of nanospheres was deposited on the surface, and reactive ion etching was used to etch around those and form these pillars, and then the spheres were etched away, and you're left behind with this forest of nanopillars. And so what's shown here is measured reflectance from bare silicon versus nanostructured silicon. As you can see, there's a dip in the reflectance that goes through a minimum, so you have, it basically acts like an anti-reflection coating. And what's shown are comparison with the dash curves are the experimental results, and the solid curves are calculations using full wave electromagnetic simulation. So this is based on the finite difference time domain method of solving Maxwell's equations. So it's a time domain solver, and then once you solve this over a certain time, you can Fourier transform it, look at the frequency response. In any case, this corresponds to different bare silicon and two different heights of silicon nanopillars, and you can see, except for the fact that there's more features in the electromagnetic solution because it uses ideal, basically very sharp structures, there's a good agreement between the simulated reflectance and the actual measured reflectance. Next, I want to talk about something called intermediate band solar cells, and I already mentioned this in terms of different types of advanced concepts, and the intermediate band concept, as I mentioned, is similar to multi-junction in the sense that you are introducing multiple levels, and those multiple levels allow you to absorb different parts of the spectrum and utilize more of the entire solar spectrum than a single gap system would use. And what's shown schematically down below are the energetics of two realizations of this, one involving basically quantum dots embedded into a matrix of a host material, and another quantum wells. The one on the right can be grown basically, as I mentioned, by epitaxial growth, and that you can grow wide bandgap material and then grow narrow bandgap material and grow wide bandgap material again. And that introduces then narrow gaps or narrow levels inside of a material with a larger bandgap. Quantum dots can be grown in the same way, and I'll discuss a way that that's realized using molecular beam epitaxy. But the main idea is that, this superlattice of quantum dots or quantum wells, because of quantum confinement, has an energetic level, which is shown here, or these levels E1, E2. Anyway, there's a series of levels, and this level then acts as the intermediate band for allowing the electron to park itself when it's excited by a subband gap photon. In other words, as shown here, a photon with a photon energy less than the band gap between EC and EV of the host material can be promoted to this level, and then a second photon can be absorbed, promoting it to the conduction band. And so in this two-photon absorption process then, you basically absorb photons below the band gap, but you basically generate electricity, or you produce a voltage that corresponds ideally to the valence and conduction band of the wide band gap material. So you get the same open circuit voltage, but a higher current essentially. So this, of course, depends on many things having to happen simultaneously, and to date, practitioners in the field have not successfully improved the efficiency. They've come close to realizing the efficiency of the material without the intermediate level, and all signs point to at some point being able to demonstrate this. But in any case, there's several things that have to be have to happen simultaneously, and one is that basically you have to have separate. This level has to be out of equilibrium with the electrons and holes in the conduction and valence band, which is practically hard to achieve because of the microscopic scattering processes that I talked about before. This is how one can realize or grow a basically intermediate band material using quantum dots. I already discussed basically that you can form quantum dots during epitaxial growth by growing strained layer material on top of the host material. And these form quantum dots. So in a particular implementation of this, the host material is gallium arsenide, which has a band gap of 1.4. Indium arsenide, which has a band gap of about 0.5, is grown on top of that and forms these nanoparticles. With confinement, the energy of the indium arsenide nanoparticles becomes closer to that of silicon, like 1 eV. And so you have an intermediate band formed by the indium arsenide quantum dot inside of a gallium arsenide host. And so you can grow these epitaxially. You grow first a layer, a wetting layer, and then it forms a three-dimensional structure. And then you cap it again with another layer of gallium arsenide. And you can do this successively. And what's shown on the right here is basically a structure that was grown by a group in Japan where this is a group in Spain which grew they repeated this process many, many times, and basically the dots line up on top of each other. So what's shown here is basically an individual quantum dot grown by this method. So this is an indium arsenide quantum dot embedded in indium phosphide. From a top view, what you see is that these are random in sense of their location with respect to one another. You can see that the size is relatively uniform, which makes this useful. The size of these individual quantum dots are fairly uniform. And you can control the size by things like temperature, the flux of material, and of course, what type of material and what kind of strain you have present. So these are grown again using techniques like molecular beam epitaxy, which are relatively expensive. Molecular beam epitaxy is done in ultra-high vacuum. You start with a vacuum less than a vacuum of outer space, like 10 to the minus 11 torr, and then you basically co-evaporate these species in this ultra-high vacuum to form the layers. So this is how an implementation of intermediate band solar cells. Another approach is using quantum wells. Okay, as I mentioned, quantum wells also introduce intermediate levels, and so this is again, you can think of this as being, say, gallium arsenide, and these are indium gallium arsenide quantum wells, which have a smaller band gap. Contact is made to the gallium arsenide, P and N, and that basically ultimately can control the voltage. But you excite electron hole pairs within the well, and either they can escape by thermal activation or they can escape by being promoted by another photon out of the well. So this intermediate band, or this quantum well solar cell, has an architecture similar to an intermediate band solar cell. And ideally then you should have an improvement of efficiency because while having the open circuit voltage associated with the gallium arsenide material, you get more carrier collection and higher current, which would lead to a higher efficiency. So some of the modeling that we're involved with, and in partnership with the University of Houston, Alex Freundlich's group there is looking at, first of all, the electronic structure of these wells using new materials. Instead of using gallium arsenide, using what's called the dilute nitride material, gallium arsenide and a small quantity of nitrogen, which allows you to tune both the band gap and to tune the lattice constant so that you can actually get better lattice matching during epitaxial growth. And these are calculations and, again, evidence of sort of a multi-scale approach. We model the electronic structure, then we model, basically using Monte Carlo, the carrier relaxation dynamics. In other words, how fast do carriers move out of here and how fast are carriers captured? This is a plot of the escape rate. And we feed this information then into a continuum model, such as the drift diffusion or hydrodynamic model I mentioned earlier, and you use that to calculate the current voltage characteristics. So we use that escape time that's simulated microscopically and use that then into a macroscopic simulation to simulate the current voltage characteristics and look at the predicted improvement of the efficiency based on different assumptions or different lifetimes assumed for this escape process. So this is just an illustration then of sort of a multi-scale approach to this. And we use basically different approaches for calculating the electronic structure. Right now, we use, for example, what's called sp3d5s star tight binding, which is atomistic way or molecular orbital way of calculating the electronic structure by looking at the overlap of atomic orbitals to form the semiconductor band structure. And this is calculations showing for example, the effect of nitrogen. So this is gallium arsenide, and this is gallium arsenide with a dilute quantity of nitrogen. And you can see that it introduces an additional level, which it introduces a lower band gap, so it makes the effective band gap lower. This is a plot of different experimental results for the band gap of gallium arsenic nitrogen with different nitrogen mole fractions, and this is the calculation using the sp3d5 star method, and just showing that you can get very good agreement. So this is then sort of the approach to the electronic structure as well. Okay, so I want to talk now about multi-exciton generation or multi-electron generation, and as I mentioned, the idea of the multi-generation multi-electron generation solar cells is basically to take the high energy photons that excite electrons to very high energy, and instead of those electrons have a chance to relax by thermal processes, they kick up a second electron hole pair and double the quantum efficiency. So this can only happen if this impact ionization rate is much larger or much faster than the thermal relaxation rate. So there's a competition between the ultra-fast carrier dynamics of energy relaxation and that of impact ionization. And so you have to have favorable conditions in order for this impact ionization rate to be fast and this process to be slow. Practically speaking, this can't be realized in bulk semiconductors because bulk semiconductors like silicon have to satisfy energy and momentum conservation, and what happens is that the threshold for this process to occur is pushed up in energy to such a high energy that it's outside of the range of the solar spectrum and practically useless. However, for quantum dots, it turns out to be quite effective, as I'll talk about in a minute. This just shows the calculation of the detailed balance efficiency that I talked about before, the Shockley-Queisser calculation, if you modify it for the effect of multi-carrier or multi-exciton generation. What's shown in this curve is basically the Shockley-Queisser curve I showed before, which has a maximum of about 33.7%. So this is assuming no multi-exciton generation. And now if you put in different thresholds, if you assume that electrons at twice the band gap can produce an additional electron hole pair, this efficiency moves up quite a bit. As you can see, it moves up to be over 40%. So simply by including the effect of the possible effect of creating a second carrier by high energy photons, the maximum efficiency immediately jumps from 33.7% to over 40%. And notice also that the band gap shifts down lower. Instead of being between 1.1 or 1.2 and 1.4, it's now shifted down to about 1 eV. And if you go to higher, if you allow multi-exciton generation to occur at 3 times the band gap and 4 times the band gap, the efficiency can go even higher, closer to 45%. So this is of interest then in improving the efficiency of even conventional solar cells like silicon, if one could introduce multi-exciton generation into silicon. As I mentioned, practically speaking, in bulk silicon, this isn't feasible, that we don't get a strong effect. And that's illustrated in this picture down below. This is research work from Matt Beard's group at NREL. And it's a comparison of the quantum yield, which is the number of electron hole pairs created per photon, measured optically. So this is an all optical experiment. This is basically bulk silicon. And as I mentioned, bulk silicon, instead of having a threshold at twice the band gap of silicon, there's no multiplication effect until you get above about 3.5 electron volts, which is basically at the end of the solar spectrum in terms of the UV portion of the solar spectrum. On the other hand, if you look at silicon quantum dots, so if you fabricate silicon quantum dots either by colloidal assembly, as I mentioned, or growing them in a matrix of silicon dioxide, these silicon nanoparticles with different diameters, 3.8 nanometers, 9.5 nanometers, basically show a threshold which is higher than that of twice the band gap of bulk silicon, and that's because you have confinement. Because you make a nanoparticle, the energy band gap is increased, so twice the energy band gap is slightly higher here. But then there's a sharp threshold, and the quantum efficiency jumps up, not perfectly, not step-like, but it jumps up to about 200% here, and then it keeps on going, and you can see that silicon nanoparticles show basically an effective multi-exciton generation. And so there's a lot of interest in can we make silicon solar cells in which we introduce silicon nanoparticles and get multi-exciton generation. Another approach, and that's one which is going on at the Technical University of Munich and which we've been collaborating with in terms of modeling, is to use nanowires. And so this is a picture of a self-assembled nanowire. Again, it's a microscope picture which shows the crystalline structure of the nanowire. And this is basically a cross-sectional view of the nanowire in which a nanowire of gallium arsenide has been grown, and then aluminum gallium arsenide has been grown around it to make a heterojunction, what we call a coaxial heterojunction nanowire. So these are of great interest right now for optical applications, for making high mobility transistors. But in terms of solar cells, there's also interest because I've already talked about the improvement of the optical absorption because of making nanowires and arrays of nanowires that you can localize the electromagnetic modes. You can also enhance the collection or excitation of electron hole pairs and possibly get multi-exciton generation. And this is just a kind of schematic of that. So if you have a nanowire in which you have a narrow gap material in the middle of the nanowire here, and you have a wider band gap material forming the cladding layer, the electron hole pairs that are excited in the cladding layer before they fall down can basically lose their energy and excite an electron hole pair by the multi-exciton process. And in fact, there's been experimental work recently that's shown that multi-exciton generation is quite strong in semiconductor nanowires, and therefore this is an approach that's of great interest. This is basically modeling work that our group has been involved with, and it just shows first the calculation, again using this tight binding representation, this sp3d5 S star approach to the electronic states in a nanowire. So this is basically the conduction band states in a indium arsenide nanowire. And as you can see, the structure is quite complicated because you have many, many different levels, and because of the bulk band structure that's superimposed on it, there's a number of inflection points. And basically this is the lowest confined state, and this is the next confined state, and the band gap of the indium arsenide nanowire has been moved from the bulk band gap of about 0.5 up to all the way to 1 eV. So just because of confinement, the energy of this nanowire, the band gap of this nanowire has been increased. What's shown on the right is the calculated scattering rates that are done quantum mechanically based on this band structure. And they're compared to the bulk band rate. I showed this before, and it just shows that as you go to higher and higher energies, you have many, many levels in the nanowire, and that asymptotically approaches the density of states of the bulk system, and the scattering rates then look like a piecewise continuation of that. So we use those rates in Monte Carlo simulation and look at the relaxation dynamics. So these are some of the effects because of the confinement. As you increase the confinement, so as you make the nanowires narrower and narrower, the mobility degrades, and the mobility degrades because as you squeeze the electronic states more and more, the effective mass increases. So you get a degradation of performance in terms of the transport. But what's more important is if we look at this curve down here, okay, this is a plot of the energy relaxation as a function of time. And so it's basically simulated by creating a pulse of electrons at high energy and watching how they relax with time. So this is the bulk rate, which is quite fast, but you can see that for 3 by 3 nanometer nanowire and 2 by 2 nanometer nanowires and then different excitation energies, that the rate of relaxation becomes much slower. And so in fact, you can get a 2 to 3 times enhancement or slowing of the cooling rate just by going from a bulk material to a nanowire. So this is another important aspect of basically nanostructured materials in terms of energy relaxation. That is that once you introduce quantum confinement and you quantize the energy levels of the system, the energy relaxation rate tends to be slowed down as well. And so that makes it more favorable for many of these advanced concept approaches to be realized because of the fact that you slow down the thermalization of the carriers because you slow down the scattering rate. So basically, the last topic I want to talk about is that of the hot carrier solar cell device. And I already introduced this architecture before, and that is that you have an absorber where basically there's no energy loss. The carriers stay hot, and they have enough energy to basically tunnel out or go through these energy selective contacts and be collected in a metal. So you basically have a voltage that's determined by the energy selective contacts, not by the band gap of the semiconductor in this case. So you're actually utilizing the energy of the hot carriers before they have time to relax. You're utilizing this energy, you're harvesting this energy before it's lost to thermal processes. And so there have been a number of, this is an old concept actually, it was really first proposed in 1982 by Ross and Nozick. And they used, again, this ideal detailed balance analysis to look at the maximum conversion efficiency. And as you can see, as the band gap of the absorber gets smaller and smaller, you're absorbing more and more photons, but you're still collecting at an energy that's determined by the energy selective contacts. And so the theoretical efficiency goes all the way up to the maximum theoretical efficiency of 86%. So that would be great if we could achieve that. The problem is that the ability to capture or keep the energy of the electrons in this absorber is extremely difficult. In bulk materials, it's practically impossible because the energy loss rate occurs at, or the rate of phonon emission occurs at a sub-picosecond time scale. So there isn't even time to get out of the contacts. These are just some of the effects that affect the relaxation dynamics in semiconductors, but I think I've already talked about these in terms of intercarrier scattering processes, different phonon modes, impact ionization, Auger recombination. So these are all mechanisms that we include into Monte Carlo simulation to study the relaxation dynamics. This is a schematic of what happens at short time scales in terms of carrier dynamics. This is partly Monte Carlo simulation, but this is also observed in in ultra-fast or femtosecond optical spectroscopy, where one can actually study the evolution of the distribution function of the carriers with time. So if you pump semiconductor material with a laser with a certain energy that corresponds to h nu equal to this separation, this is the conduction band, and this is the conduction band, and this is the valence band. Initially, you create a population of carriers that's completely out of equilibrium. The electron energies are up here, the whole energies are down here, and they have nothing to do with the energy of the absorber or the crystal. And then as a function of time, these carriers interact with one another, they exchange energy, they scatter, and basically broaden into a sort of Maxwell-Boltzmann distribution. In fact, this is the process that's involved in when a system starts out at non-equilibrium and evolves to equilibrium. It goes through this process of thermalization in which energy is exchanged among the particles, and it goes from a completely non-equilibrium distribution to basically a sort of classical distribution like a Maxwell-Boltzmann, or for electrons it would be the Fermi-Dirac distribution. So there's a time where you have equilibration, but you have basically equilibrated distribution, but at a temperature that's much higher than the lattice. So it's still hot. You have this distribution of carriers, but their average temperature is much higher than the temperature of the lattice. And then over a longer time, they cool by emission of phonons, and this becomes a Maxwell-Boltzmann distribution, but at basically the temperature of the lattice. And at very long times, so this is basically picosecond, this is tens of picoseconds, and now we're talking nanoseconds when we get to this point. That's when recombination starts to take over and the population decreases because electrons recombine with holes and give off photons or thermal energy. And this is just Monte Carlo simulation showing that effect going on. This is, for example, the electrons distribution function at snapshots corresponding to this, which corresponds to this what's called athermal distribution. And then after a short time, this basically evolves into a sort of Maxwell-Boltzmann tail. And that's all due to carrier-carrier interactions, which are very fast. So this is sort of the hot carrier dynamics as simulated. And now when we talk about quantum confined systems like quantum wells, nanowires, and quantum dots, this relaxation dynamics it can be slowed down. It can be slowed down because while in a bulk system you have a continuum of states that are available to scatter to, if you have a completely quantized system like a quantum dot, where you only have discrete levels, then it's impossible for an electron to basically emit a phonon and go from this level to this level and conserve energy. So this basically is a simple way of explaining why, because of the density of states effects, that thermalization can be slowed down. So we have a much better chance in sort of nanostructured system or quantum confined systems of slowing down energy relaxation and getting higher temperatures that you would need in order to realize this hot carrier solar cell concept. Another idea is that has been proposed primarily by the University of New South Wales group is that maybe we don't have to worry about the loss of energy of the electrons if we don't lose the energy of the phonons at the same time. In other words, if you keep the heat in the system, so if you could make a sort of thermal reservoir, the energy that's lost by the electrons would stay in the phonons. Those phonons could be reabsorbed by the electrons, and the electron phonon system would stay at some elevated temperature. And this is the idea which is called non-equilibrium phonons, which is another approach to trying to keep that energy in the system. So again, the idea in this particular case is that when electrons emit an optical phonon, which is the primary energy loss mechanism, optical phonons have a very slow velocity and they hang around, and so they don't leave the system. And it's only when an optical phonon decays to an acoustic phonon, and acoustic phonons, just by their name, are what carry sound. Acoustic phonons are responsible for the propagation of sound within a crystal. And more importantly, they're what carry heat away from a certain area. If you have a hot spot, acoustic phonons carry the heat away. So if you can prevent the optical phonons from decaying into acoustic phonons, you can keep the energy in the system, and this is the so-called non-equilibrium phonon approach. And there are certain materials, indium nitride, for example, in which the separation between the optical modes, which are these modes, and the acoustic modes, which are these modes, is separated by more than an optical phonon energy. So therefore, there's no direct channel for an optical phonon to relax and become an acoustic mode. So that means that you can get relatively long lifetimes, theoretically. And this is just Monte Carlo simulation showing that as you increase the phonon lifetime, that the temperature, this is the energy as a function of time when you create a pulse of carriers and simulate their dynamics. And instead of relaxing to the lattice temperature, they relax to a temperature that's higher depending on the phonon lifetime. So this is evidence that you can possibly with hot phonons achieve temperatures that might be useful for a hot carrier solar cell. There have been some recent experiments in which, in multi-quantum well structures, for example, the group in Paris, Labrie group, has shown that in this multi-quantum well structure, under monochromatic optical excitation, that depending on the absorbed power, that you get an increase in the lattice temperature as measured spectroscopically. So this was the structure, and what's shown here by the diamonds, these are the experimental points. So as the absorbed power goes up, the measured carrier temperature spectroscopically increases. So they start at 100 degrees, they get up to about 250 degrees. And this has then been modeled by our group, which shows that assuming different phonon relaxation times, going from 2 picoseconds to 50 picoseconds, that you get a good fit with a phonon lifetime of 15 picoseconds, which is not unreasonable to be able to achieve in, say, a layered structure system. So this shows at least that you can get some enhancement of the temperature that would be useful for hot carrier solar cells. Unfortunately, at this point, what you need is a temperature that's closer to 1,000 degrees Kelvin in order to really see the benefits of the energy selective contacts. And so at this point, it's still a research topic. It's not so far a practical solar cell, but it is a solar cell like the other ones that has a pathway to basically achieving high efficiency. So I've talk today about a number of different technologies, first giving you an overview of photovoltaics and then talking about some advanced concept approaches that utilize nanotechnology and their implementation that provide pathways to achieving high efficiency. And so basically what I've talked about is how nanostructures can provide those opportunities by quantum confinement, by surface effects that give you new energy levels, and also basically provide control of some of the relaxation dynamics that limit performance of solar cells, in particular energy cooling. These basically are long-term type of solutions, and ideally they would be disruptive, but we also are looking for short-term solutions that would basically implement into conventional technologies and improve the efficiency. Light trapping, for example, is one of those. Being able to introduce, say, multi-exciton generation into a conventional silicon solar cell would be another way of improving the efficiency above the Shockley-Queisser limit and improving module efficiencies. Anyway, the bottom line, as you can see, is there's many different material problems and challenges, which are, of course, very good for research and collaborative research. In particular, a number of advances have to be made in materials, in physical understanding. It takes new types of approaches to modeling and simulation that require multi-physics, multi-scale approaches to bridge the vast timescales and length scales that we have in typical photovoltaic devices. And basically we have a number of challenges in terms of controlling the properties of surfaces, mitigating the effects of surfaces in terms of recombination, and improving the performance of solar cells, hopefully to newer and higher efficiencies. So thank you for your attention, and that's my seminar.